Welcome to Electromagnetism Part 5. In this video, we'll be discussing how to determine the magnitude and direction for the magnetic field created by a current-carrying coil of wire, which is also called a solenoid. Taking a look at the key pieces of information here, we have the magnetic field, B, created by a current, I, carrying coil of wire. And we'll talk more about the coil here in a second. The magnitude is simply an equation that we'll get out of the way right now. And to do that, the strength of the magnetic field depends on the vacuum permittivity constant, mu naught, little n, which we'll define here in a moment, times I. It makes sense to us that if we increase the amount of current, that the strength of the magnetic field increases. And we'll cover all the factors that control the strength of the magnetic field of a solenoid here in a moment. Little n is the number of turns, which we'll call capital N, per unit length. So n is the number of turns, and L is the length of the solenoid. So you can see what we're going to do here in this case is we're going to take instead of it being a straight wire, we're going to take a wire and we're going to wind it around some kind of core. And that's what this rectangle represents in this diagram. It represents the core of the solenoid. Okay? So how do we depict this on a two-dimensional surface? It's a little tricky, winding a wire around there. But what we do is we take and show the winding around the core where the breaks in our spiral are the parts of the winding that is behind the core itself. We can pick randomly which end we're connecting to positive, which we're connecting to negative. We'll pick this end to be negative and this end to be positive. And with conventional current flow, that means it would be flowing away from the positive. The current through this wire wound around this core would be away from the positive and toward the negative. You don't have to draw all these arrows, but I'm just going to do that for the lesson here. You don't have to do this every time, but it really hits home for you how that current is flowing around the solenoid from the positive end to the negative end. What we use to determine the magnetism created by this is a hand rule that looks very similar to the first hand rule that we discussed with a magnetic field created by a current-carrying wire. And that is where your thumb sticks out the side of your hand, your right hand, and your fingers curl in the natural shape of a C. But in this hand rule, the digits reverse roles. So in this hand rule, for direction, your fingers this time curl in the direction of the current flow, and your thumb points in the direction of the north pole of the magnetism. Okay? So that's how this hand rule is used to determine the direction of the magnetic field created by a current-carrying coil of wire. Okay? So if we take a look at this particular sample, we can see that the current goes behind the core and over the front. So if you can take a look at using the hand roll this way on your right hand, you should be able to see that the current goes behind the core and over the front, and your thumb ends up pointing to the right. That makes this the north pole of that electromagnet, and it makes this the south pole of that electromagnet. This essentially now becomes the same as the magnetic field for a bar magnet. So if we were asked to draw the magnetic field for this, we could do that easily. And that would be away from the north towards the south. And we could do that again for another set of lines here. Away from the north towards the south. Again, be careful that your lines don't cross along the way. And what's really neat about this, and you'll see questions like this, they like to ask a lot about the direction of the magnetic field inside the coil. And of course, we've already talked about that in a previous video, how it goes away from the north towards the south inside the coil itself. To wrap up this discussion, I think what we're going to do here is talk about what factors increase the strength of the magnetic field so we'll label this factors that increase B. And if you think about it, there's really three things you can do here. One is to increase the current. So put increase I. That could be accomplished by a number of ways. You can increase the voltage. You could decrease the resistance by lowering the temperature. Use a material with a better resistivity. All those things end up increasing the current there. A second way to do it is to increase, if you look at the equation, it should make sense, is to increase little n. What would be the way to do that is to increase the number of turns, or take the same length of wire and decrease the length of the solenoid itself. So you want to increase the number of turns per unit length, and you're going to do that by using a longer wire to get more turns, or by using the same length of wire and decreasing it by decreasing the length of the solenoid itself. The third one is to use a ferromagnetic core. So instead of just taking and winding our wire around a stick or a pencil or a cardboard tube, if we insert a ferromagnetic core, such as a piece of iron or a steel bolt, which has iron in it, we would be able to increase the strength of that electromagnet as well. All right, so this ends it for magnetic field created by a current-carrying coil of wire, and we'll have several problems remaining in the problem set that deal with this concept.